Hello guys, welcome back to my YouTube channel. I am Suprita Kar, currently pursuing BE in Sri Venkateshwara College of Engineering, Bangalore. I am currently pursuing third semester in the branch of Artificial Intelligence and my USN is 1VE 23CA045 and today's course title is Digital Design and Computer Organization and today's course code is BCS 302 and in this video we are going to discuss about introduction to K-mapping. Let us see what is an introduction to K-map. K-map means or K-mog are a visual tool used in a Boolean algebra to simplify logical expressions. They are a graphical representation of two tables, making it easier to identify and group terms that can be combined to create a simplified expression. K-maps are particularly useful for simplifying logic expressions with up to 4 input variables. They are the key tool in a digital circuit design, allowing for the optimization of a logical circuits, leading to more efficient and cost-effective designs. Let us see what is a definition of K-map. A K-map is a diagram that represents a Boolean function as a grid. Each cell in the grid corresponds to a unique combination of the inputs, and the value of the cell represents the output of the function for that combination of inputs. The cells are arranged in a specific order such that adjacent cells differ by only one input variable. This arrangement makes it easy to identify groups of adjacent cells that represent terms that can be combined to simplify the function. As you can see in the left side, you can represent a K-map by using four grids. Let us see what are the properties inside a K-map, that is input variables, output values and a grouping adjacent cells. The K-map has rows and columns representing the input variables and their possible values. For example, a two-variable K-map has a two rows 0, 0 and 0, 1 and two columns 0, 0 and 1, 0 to represent all possible combinations of a two input variables. It goes on as you take the variable increases like 3 variable and a 4 variable and the input of a rows and a columns also differs like 0, 0, 0, 1, 1, 0 and 1, 1 goes on. Output values. Each cell in a K-map represents a unique combination of input variables and is labeled with a corresponding output value, usually 0 or 1. This output value corresponds to the function's truth table entry. Grouping adjacent cells. The key to simplifying expression in a grouping cells that one value. These grouping represent terms that can be combined to simplify the function. The group must be rectangular and have a powers of 2, that is 1, 2, 4, 8, etc. cells. Let us see what are the advantages of a K-map. First one is visual approach. K-maps provide visual representation of the logical function, making it easier to understand and manipulate the expression. This visual approach can be particularly helpful for beginners learning Boolean algebra. And the second one is simplified expression. K-maps are designed to help identify and group adjacent terms that can be combined to simplify the Boolean expression. This leads to more compact and efficient logic circuits. And the third one is easy of use. K-maps are relatively easy to learn and use, even for a beginners with a limited experience in a digital logic design. The process is straightforward and intuitive, making it accessible to a wide range of users. And the last one is error detection. This visual nature of a K-maps helps to reduce the risk of errors in the simplification of process. The grouping of terms in a straightforward, reducing the likelihood of overlooking and misinterpreting any terms. Let us see our disadvantages of the K-map. First one is limited input variables. K-maps are typically used for simplifying expressions with up to a 4 input variables. Creating a K-map for a function with a 5 or a more variables becomes difficult to visualize and a manual process. The simplification process using a K-map is largely manual, requiring a careful attention to detail and the identification of all possible groupings. These can be a time consuming, especially for a complex functions. And the last disadvantage of a K-map is limited optimization. While a K-maps can lead to simplified expression, they may not always yield the absolute minimal expression. It's possible to find alternative groupings that can result in even simpler expression, but this requires additional effort and analysis. Step-by-step process of a K-map. Let us see what are the steps to solve the K-mapping. First step is construct the K-map. Start the creating a K-map with the appropriate number of cells based on the number of input variables. Example 2, 3 or 4. Each cell corresponds to a unique combination of input variables. Label the rows and the columns with the input variables and their values. This is going to be a second step. Fill the K-map. Enter the output values of the Boolean function in the corresponding cells of the K-map. These values are usually 1 or 0 depending upon the function truth table. And the third step is group adjacent cells. Identify groups of adjacent cells that contain one value. These groups should be rectangular and have a pairs of 2, that is 1, 2, 4, 8, etc. cells. The goal is to find the largest possible groups as this will lead to the simplest expression. And the last step is write the simplified expression. For each group, write down the corresponding term in the Boolean expression. This term is formed by the considering the input variables that remain constant with the group, and these terms using OR operation to form the final simplified expression. As you can see, the left side is an example for creating a step-by-step process of K-map. Applications of a K-map. It is control systems, designing logic circuits for control systems in a various applications, including a robotics, industrial automation, and traffic signals, and cryptography. Simplifying the logic expressions for encryption and decryption, algorithms used in a secure communication and systems, and other applications are digital logic design and a computer architecture. Limitations of K-map. K-map have a limitations that prevent their use in all the situations, that are complexity, manual process, limited optimization, and don't care conditions. Here, the don't care condition is an important. K-maps can handle don't care conditions where the output of the function doesn't matter for the certain input combination. However, effectively utilizing these conditions require careful consideration and undergoing logic functions. Let us see the conclusion and the key takeaways of these K-map. K-maps are valuable tool for simplifying Boolean expressions, particularly for logic circuits with up to 4 input variables. By understanding the advantages and the limitations of a K-maps, engineers can utilize them effectively to design efficient and optimized logic circuits for a wide range of applications. This is all about a K-mapping. Thank you for watching my video. Please like the video and subscribe to my channel. Thank you.